and welcome to my session. This is a demo-only session on building a serverless data handling application. And since it is pre-recorded, I've decided to do all the demos and then do a voiceover and tell you what you're seeing afterwards. So don't be alarmed if you can see both my hands working on the screen while at the same time clicking the mouse in the window. This is to be expected, and this is just to try to give you the best possible experience. So let me first introduce myself, and as this is a demo only no slide session, I will use Dryo to introduce myself. My name is Benjamin Kettner. I'm CTO at MLPA Consulting GmbH. We're a small consultancy based in Berlin, Germany. We're a cloud-first company, so we focus on cloud projects and mostly on IoT projects. My email address is benjamin.kettner@mlpa.com, and you can use this contact information to get in touch with me at any later point. So let's first talk about what we're going to do today. Today we're going to talk about a data handling application, that is an application that deals with data. And we want to deal with an application that deals with data in a serverless way, meaning we want to create an application that processes data in a serverless way, and we'll talk about serverless at a later point. So first, let's create a draft of what our application could do. The application I have in mind is an application where we develop a mobile application, a mobile phone application, and this mobile application is a store aggregator that that you can use to connect to different stores to purchase the items that you like at the lowest price. So what this mobile application needs is some kind of backend that usually is a REST API that it can communicate with, and that it can get data from. Since we're dealing with a data handling application, dealing with data is very important. So our application needs to communicate with the backend, send data to the backend, receive data back from the backend. So that's the first bit about our application. Now, of course, this backend needs to query its data from some source, from some store, because the backend itself should not hold any data. So what you want to do is you want to connect that backend to a data store, and of course the data store you can use for that is a database. So we'll add a database here, and the database we will add is at the moment a relational database, meaning it is a database dealing with tables and relations between tables. And what will we use this database for? If we look at it, what we need to get is, for example, information about the items that are on offer. Where are they on offer? What do they cost in the store? What are shipping terms? We need to get user details like shipping addresses, billing addresses, and we need to get information like third-party store URLs and information about the third-party stores. So this is all stuff that our REST API will need to query from our relational database. So this is an operational database. Actually, in the end, this is an operational database that contains information that we need to run our application. And of course, we need the store websites that we want to communicate with, the external stores that we want to get or submit orders to, and we'll need to communicate with those using APIs of the stores. So this will be some store native stuff. So we'll use APIs to communicate with the external stores. So these are the main components for running the application and displaying stuff to the user and implementing the base functionality, namely ordering stuff from external stores. Everything driven by a REST API backend. The next item we want to add here is a second database. Now, the information we get from the external web stores, like an order confirmation, will not be in any schema that we are aware of. So it will be a schema for each store. So to try to push all that into one unified schema will be quite difficult. So what we want to do is, if we have order confirmations, if we have information about orders, store the completed order information transactions in a NoSQL database so that we can store them in the format that the external website offered us. So we'll need something like a schema, a database without a schema, so a NoSQL database for that, in order to have the transactions as they are created on the external website. Finally, let's add another tool, another thing that we need. Another thing that we need is a data lake storage. And you might ask, why do we need a data lake? It's fairly simple. As the user uses our app, he visits certain product pages and everything. And if we don't track the information which pages were visited by a user, it's very hard for us to tell, to make a ranking which are attractive offers, because we don't know, was an item not bought because it was not seen, or was it not bought because the offer is not attractive. So we want to start tracking usage data. And to do that, our REST API needs to store information about what pages were queried in a data lake. And that's information that we want to work with. For the first time, this is not operational data. This is data that we need for analytical purposes in the end, when we start to improve our web shop, when we start to work with our application, with the data of our application, and when we want our application to be truly data driven. So this is usage information. And of course, we'd like to persist all this information and get all this information together in a centralized way so that we can work with it from a centralized location. And that centralized location is some kind of data warehouse. And that data warehouse, of course, needs information about orders that were completed. So it needs the purchase information from the NoSQL database. It needs information about the items that are on offer. So if there are new items added, it needs information about that. And it should probably be able to, our analytical system should be able to write data back to the relational database, for example, to offer rankings and improve the ordering of products and the display of products. And then it will also need at some point data from the data lake. So we'll need information about which pages were visited by the user, when and in which order. So those are basically the main data sources that we want to include into our analytical system. On top of that data warehouse, of course, we can do reporting, and we will do reporting to offer a view into our operations and to see what performed well, what didn't perform well, which items could we sell or couldn't we sell. So the data warehouse, apart from having an operational part where it feeds back into the operational database, will also be a classical reporting database that will display information for management, for operations, for everyone working in our organization trying to improve our application. So now we have an overview of what our application can and should do and how it interacts with which parts. So we have a rough architectural overview of the components that are required for our application. So I would like to pick this moment because the title of the talk was about serverless data handling. So I would like to take a moment now to talk a bit about serverless. What does serverless mean? Why is it serverless a topic? Why are we working with serverless? And I would like to take a moment to talk a bit about that. Now, our typical user behavior will be something like this. If you have the time axis to the right and the number of users to the top, and then create a bar chart with for the users. Then our typical user behavior will be like this. We'll start off in the morning with some rather low user numbers. Then as the day progresses, as it gets later, users start to wake up. And then in the morning, users start using apps, using their smartphones, buying stuff on the internet. We'll have a peak sometime during the morning. And then as people start to work and as their work days get busier, of course, the usage will drop again. And people will buy less and use our application less as it's not a business application. And then throughout the day, in the evening, as people start to get off work and start to get home and start to buy things again, of course our traffic will again pick up, and we'll see high usage numbers in the evening, which then drop again at night when people start to go to bed. So your typical curve of number of users on your website application will look something like this. Now, let's talk a bit about provisioning. If you were to provide hardware to run an application with that kind of user load, if you were to run it on a classical web app or on premises, what you would do, you would probably provision a virtual machine or compute power that is scaled. So like the green box you can see now, that will be scaled like the green box you can see now, where you say, okay, I need to provision enough compute power to cover the peaks and to deal with the peaks. And if I've provisioned it like that, I'm safe and nothing can happen. And people can start using my application, and I'll be able to deal with the load. So that will be like a classical way of deploying such an application, classical provisioning to supply such an application. So this is one possibility that we should keep in mind, that's where we come from. If you would do it in your data center or using a web app, a classic web app, you would do it something like this. Of course, you're in the cloud, because in the cloud you can scale up and down very fast. So what you would do in the cloud, if you say, I want to leverage the power of the cloud, I want to leverage the scalability of the cloud, you would do it slightly different, and you would do probably something like the blue box you'll see here. And you'll try to adapt the resources you provision for your application to the load you expect at certain times. So you probably have a provisioning where you have like a certain compute power in the morning, and then during noon you'll scale down and have much less compute power because you know that the usage numbers will go down. And then in the evening you'll scale up again, and you'll scale even bigger than at night. Early night you'll scale even bigger than you did during the day. So you'll probably provision something like the blue line shown here. And so that will be your manual scaling. If you were to scale up and down manually, you'd probably do it something like this. But now the question is, what happens if you have unexpected peaks? For example, an advert rolls in and your store is overrun with users, or for some reason an offer is rated high on Google and you'll get lots and lots of customers. Then you might be under provisioning, and if you do it in a way like this. So what might happen is that some of these peaks will run outside your boxes and cause your system to be slow, be unresponsive, and you'll lose users doing it like that. So you probably again over provision, and you probably have a lot of alerting and a lot of manual intervention to get this to scale properly. So the serverless way to do this, what you try, if you do it in a serverless way, what you would try to do is to make the subdivision of these boxes as small as possible, and tell your cloud provider, well, I don't care about the subdivision of those boxes. I just care that my application runs. So, dear cloud provider, dear Microsoft, please make it so that I have sufficient compute resources for my application. No matter how many users I have, please take care that my application runs smoothly, that I have certain response times, and please ensure that I have sufficient resources at any time. So this would be the serverless way of thinking. You don't think in service anymore. You don't, of course, there's still a server involved. You don't get rid of a server. There's still a server that runs your code. There's still a server that hosts your database. But you say, I don't care if that server needs 1 GB of RAM or 2 or 5 or 15. I just want that server to run and to be able to process the queries that are coming in. And you say, I don't want to know how many compute nodes, how much CPU I need. I just want there to be enough CPUs to accommodate the usage that I'm seeing. Not that I anticipate, but the usage that I'm actually seeing at this time. So this is the serverless way of thinking. So you could say serverless thinking means stop thinking about servers, stop thinking about compute resources, just think of your application and think of, stop asking how many compute resources do I need for my application. Rather say, I want my application to run. Dear Microsoft, you figure out what kind of compute resources we need. So how is this done if we want to do it in services? So next we need to translate our architectural overview back to Azure services that we can deploy and work with. We're in luck because many services are already available as serverless services, and there is quite a handful of services that are serverless services and that you're not even aware of that they are serverless services. So if we look in here, we'll find that we can do almost everything here in a serverless manner. So let's start talking about resources, talking about Azure resources. If we want to work with this architecture, the first thing that we need to deal with is REST API. So we need something to accommodate a REST API. And we're lucky because there is such a thing, and that's an Azure function. Azure Functions are a really flexible, versatile tool, and we'll use it a lot. And the great thing about Azure Functions is that Azure Functions have different triggers. So a function, you deploy code in a function, and that code can be triggered by different events. It can be triggered by messages being sent to a queue, or even as in this case, by HTTP requests arriving at a predefined URL. So that will be what we could use to implement our REST backend. Functions, Azure Functions with HTTP triggers. So that exists as a serverless option. And also we're quite lucky because Azure SQL database, not if you're going to the MySQL or Postgres, but if you're sticking with Microsoft SQL, Azure SQL database also has a serverless tier. So you could also deploy the database in a serverless manner. Of course, with database, it's a bit different than it is with function. For the database, basically for the function, you're just able to scale out. So you can say, okay, I just need another host running the same code. And for the database, you increase the number of nodes on the same host. So the scaling works a bit different. You can't just spin up a second host, but you have a serverless option and you can deal with it that way. Now the data lake storage. Data lake in Azure works from storage accounts v2 with hierarchical namespaces enabled. So storage accounts are, in fact, even if no one ever thinks about them like this, storage accounts are serverless entities, are serverless services. So we can add a storage account here, and if you've provisioned a storage account before, you were never asked how much CPU does the node that hosts the storage account need. You just have a storage account and you can access the storage and retrieve data from it and write data to it. You don't care how much CPU power is used here. However, we want to take this one step further, and writing directly to the storage account from the REST backend can be a bad idea because it can cause blocks, it can cause delays. So what we'll do, we'll write all the messages that arrive to a storage queue, and that's again these tracking points come, these storage queues come with storage accounts, so they're serverless just as any storage account. And from that queue, we can again trigger an Azure function using a queue trigger, storage queue trigger, and that Azure function can then take care of persisting everything in the right way in our storage account. You can do that directly from the REST backend, but often if you build an application like this, and the keyword here is resiliency, if you want the whole process to be as stable as possible, even if certain elements are not available, it's a good idea to decouple things to make things work asynchronously by adding queues in between. And we've chosen a storage queue here, but of course you could also choose an event hub or a service bus queue. So that's up to you which one you prefer or which one suits your application's needs best. However, we chose the storage account queue here, and having the function in between here is a nice thing because it will enable us to do things like add additional business logic, apply additional business logic. So we could do things like saying, okay, certain tracking points we need to forward to other systems, or we need to deal with in a specialized way, or we want to report differently on certain points. So we could say, okay, every tracking information that arrives is stored in the blob storage in raw data, but we're already prepared to get certain tracking points out of our out of that queue and process them with some logic individually. So that's also a nice thing that we've prepared by building the architecture in that way. So the next thing we want to deal with is information about orders that were made, about purchases that were made through our app. For that, we need to persist the information of the purchases that were made. And again, we want to decouple that from the REST backend in an attempt to do a separation of concerns, have the REST backend serve the data it needs, but not do everything in one function. So again, we add a queue. We can use a storage queue again here, and that will be the queue that hosts the checkout event. So this will be the checkout storage queue, and every checkout event will trigger then again an Azure function because we've already seen that pattern and we can work with that pattern again. Because that pattern is scalable and works well for our application. So we have again a Azure function that takes those checkout, that processes a checkout event, and then stores the checkout event in a database. And we said that we didn't want to use a relational database because the shape of the checkout event could differ from store to store. So instead we'll use a Cosmos DB here as database that stores the checkout events in a serialized JSON way. So basically the Cosmos DB will be used to host the schema-free checkout events that might differ for each store that we attach to our platform. So our Azure function then needs to write to our Cosmos DB, who needs to write the checkout events to the Cosmos DB. Okay, so now we've dealt with storing the checkout events. We've dealt with the normal usage of our application. Next, what we need to do is we need to talk with the external APIs. And here a speciality comes in, because if we deal with the external APIs, there's something that's important. The order of events that occur are important. If we send to an external API, first, if you place an item in your shopping cart and then remove it again, You want to end up with the item not being in your shopping cart. However, if we cannot guarantee the order of events, what might happen is that we send an event to the external store saying, remove that item from the shopping cart, and it's not in yet, so the external store would hopefully not do anything. And then we send an event saying, okay, now please add the item to the store if our events are not sent in the right order, which means we would end up with one item in the shopping cart instead of no items in the shopping cart. So here, when we communicate with the external APIs, the order of events is really important, and the storage queue cannot guarantee the order of events, cannot guarantee that events are delivered in the order in which they were inserted. Most of the time this will happen, but it's not guaranteed. And we need to guarantee that, so we'll use another queue instead. We'll use Service Bus instead, because Service Bus guarantees the order of events to be preserved when we send events to Service Bus. It guarantees that events are delivered in the right way. So we'll use Service Bus as an event queue towards the external APIs. Instead of storage queues or Event Hub. And that's also neat because Service Bus also, if you provision a Service Bus from the Azure portal, you do not get to choose CPU power or RAM or anything. You just say, okay, I want it to be able to handle a certain amount of messages, and that's it. So it's also a serverless service if you think along that line. And we can speak with it. We can queue events in it directly from our REST backend. So it's also it fits our application really well, and is easy to implement, as you will see later on in this presentation. And to that Service Bus, we can then again attach a function that has a Service Bus trigger. So already now you can see the pattern is fairly easy. You create events in a certain manner, and you have a function that is triggered by that event and then executes some code for you. So the pattern is the same for all of these things that we need to do. The pattern is still the same. However, it's done in a scalable way, and we can do this in a serverless way and make sure that everything scales. So now let's take care of the data warehouse. For now, let's start with the data warehouse as a normal Azure SQL database. Of course, we could go towards signups, but signups, especially if you go to dedicated pools, is far from being serverless. So we'll use a SQL database, which we can again provision in a serverless way, and we'll get data from all the different sources that we need to get data from using Azure Data Factory. So Azure Data Factory will query the operational database, and we'll also be able to write to the operational database if we need that. It can query the Cosmos database, and it can query the storage account, and get information from all of these different locations and persist that in our data warehouse. Azure Data Factory has a mode where you can provision your own self-hosted integration runtime, which means you need to take care of compute resources. But if you don't do that, the default integration runtime of Azure Data Factory is also serverless. You do not know and you do not care what infrastructure lies behind that. You do not need to handle the infrastructure that lies behind that. You just say, okay, I want to transform data, I want to transfer data from A to B. Please do it, and please provision sufficient resources to do so. So let's talk a bit about provisioning resources and getting resources set up in Azure. And we will not provision all the resources here in this presentation because this would just be too much for this length of presentation. I'll just give a spotlight here. However, you will be able to find ARM templates and parts of the solution in my GitHub repository at a later point after this presentation. So be sure to check it out, and this is also constantly expanded and added to, so it's worth checking it out sometime again. However, now if we want to provision the resources, I won't click them in the Azure portal. Instead, I have prepared an ARM template, and the ARM template will create some of the resources from this overview. And let's now dive quickly into what this ARM template looks like and what's in there. This is the ARM template we've prepared. The ARM template first takes a set of parameters. Parameters are things like that you define when you create your resources, like a database login, a database admin password, and I've chosen an extra secure password, as you can see, and the definition of what our UTC time, the time that we have is, and we'll use the timestamp for the tags in our resource group. And so we can supply default values for the parameters. From the parameters, we can derive certain variables like the storage account name, database server name, database name, function app, service plan name, function app name, and the tags that we want to write to each resource, and that contains the UTC time, as you can see. So next is the resources we want to create. The first resource we want to create is a storage account, and you can see that the storage account is of type storage accounts. No big surprise here. And it has the name that is defined in the variables. It contains the storage blob plus some unique string that is globally unique, that enables all of us to use the same ARM template without creating problems for the same names. And you can see that we apply the tags to our resource as well. The location is inherited from the resource group. And as SKU, you can see that we use a standard locally redundant SKU. This is only for demoing purposes. This will easily suffice, and you can see in the properties in line 51 that hierarchical namespace is enabled for this storage account. So this means that it has the data lake extension installed and can be used as data lake, and will allow us to create arbitrary folder structures in the storage account. Then in the storage account we create stuff like queues and everything, but we don't need to take care of that now. Next thing that's really important and interesting is the SQL Server in the database. So first we need to create a server. The server is, of course, as you have already assumed and seen, of type Microsoft SQL/servers. It contains a database, which we'll look at a moment. The tags are again given, the location is the same as the resource group, and our name is again derived from the variables. Now, it might seem like a bit of a contradiction to create a server in a serverless environment. However, the server is basically the container that enables us to connect to the database. So the server defines the URL, and so that's what we need the server for. Next, in the server, we create a resource, the database resource. And the database depends on the server, as you can see. It has a name that is derived from the variables again. It also contains the tags from the variables that you've already seen before. However, the interesting thing is the SKU we use, and the SKU is general purpose serverless. So the S stands for serverless generation 5. So this is a serverless SKU, and it uses a capacity of 4, which means it's deployed using 4 nodes. However, we also define a min capacity. So we say, okay, it can scale down, or it can start with as little as half a node. And after 60 seconds of delay of nothing happening on our server, it will automatically be paused and stop costing money except for the money you pay for the storage. And this is where it gets serverless, where you define a minimum capacity and a maximum capacity and tell Azure just scale my database somewhere between those capacities as required by the load. Next, we create a app service plan for our function. The app service plan is like the server for the SQL database. It's the container that hosts the function. And you can see that the SKU we use is a Y1 SKU, has a name Y1, and is in the dynamic tier. And the dynamic tier means that it's a serverless, that it's a consumption plan that we're using. So this is basically the serverless way of creating a function app service plan. You could also use a premium plan. Premium plans are also serverless plans, with the difference that they have warm spares, warm standbys, and not cold. So they scale a bit differently, and the cost is calculated differently. However, for our purposes, for our demo purposes, consumption plan is fairly sufficient and was sufficient for most applications that I've seen so far. Then we create a function app that depends on the app service plan, of course, because it's located in the app service plan. And we can set some app settings for that function app. App settings like link it to a storage account, tell the app service what kind of function it is, what runtime it uses, what version of the functions environment it uses. So there's certain settings that we can make directly when deploying the template. We'll use .NET as a runtime because .NET is vastly supported and is a great option for writing Azure Functions. Next, we want to deploy that template. And there's different ways to deploy an Azure template. If you're pulling this from GitHub, you'll find a deploy to Azure button on the repository, but you don't need to do that. I've prepared a resource group in West Europe, which is the location closest to me. And now I want to deploy to that resource group. And I can do that by adding a template deployment resource. So let's go over here, copy the entire code of our template, and then go back to the portal and say, okay, we want to create a template deployment. So search for template deployment. And now you've found the template deployment, and you can create a template deployment. And here you can say build your own template in the editor and just paste your template code that you've just copied. And you'll see on the left that you can see an overview of the resources that will be created, also the nested view. But if you click Save Now, then in the next step, you'll be asked to fill in the parameters that were defined in our template. I leave them all at default here for demoing purposes, but I would recommend, if you do it yourself, that you change the admin password to something a bit more sensible than what we've used here. Now if you click Create, then all your Azure resources are created. This takes some waiting, and after we've waited sufficient amount of time, you'll end up with Azure resources in your resource group. So now our deployment is complete, and we can click to go to our resource group. And let's have a look at the resources we've created. It's not a big surprise. You have the app service, and you can see that there's the string that makes my resource names unique. You have the function app, the SQL server, and the storage account. So let's first look at the function app. And you can see that the function app is running on an app service plan that is Y1. And if we click on that app service plan, we can see that it is a serverless plan, and we can see that because on the left hand side in the menu, scale up and scale out are grayed out. So we cannot scale the app service manually because we're in a consumption plan, we're in a serverless plan, and Azure will take care of the scaling for us. Now if we look at the database, at the database server, you can see the database server here, and if now you can see the tags that we've created with the date for the creation. And if we look at the database, if we go into a database you can see that it is a general purpose serverless generation 5. So this S was the serverless, and it has 4 vCores. And if you look a bit deeper into the database, you can click the pricing tier to find out how is it scaled, and you can see that it has a max of 5 vCores and a min of half a vCore, which is what we set in our template, so it's not very surprising that this happened. And you can see the auto pause after 60 minutes, just as we've designed it. So these are the serverless services that we've created with our template deployment. So everything is here just as we wanted it to be. The database is, by the way, paused when we started. So let's now pull up Visual Studio Code to create a new Azure function. For that, first we create a new directory in our terminal in which we want to create our function. So DPS 2021, change to that directory. And now we can use the CLI to create functions and everything around that. And for that we use func_init, which inits an Azure function, and we give that function a name and we call it serverless talk functions. And if we do that, we get to choose the runtime, and we choose .NET. We could also choose the runtime by adding --.NET to the call. We could pre-choose the runtime, but you can also choose it from the select here with the arrow keys. Now we've created the serverless function, and that has created a directory in here that's called serverless talk functions. And if we go in there and look in there, there's a host JSON, a local settings JSON, and a C# project file. So nowhere to put our code yet. And for that, basically what we've done now is we've created the wrapper that will hold the code later on, that can hold several functions. And what we need to do next is we need to create a new function. So we say func new, and we give our new function a name, and the name that we will use we can pass with --name on the command line, and we'll call that tracking input. So this will be the tracking input function, and we can use a template for that, and the template we'll use is a HTTP trigger. So this will create a function with an HTTP trigger, and we'll use the authentication level anonymous because we want to be able to access that function even without authenticating previously, or without passing some keys. So now we've created the function, and if we look into our directory now, we see the tracking input C# source file. So let's now open up the entire directory in Visual Studio Code so that we can work with all the files. So let's open the folder. The folder we want to use is, of course, the Azure Function folder from our home directory that we just created. So let's go to the home directory. Let's choose DPS 2021. And in here, let's open the serverless talk function and select that folder. Once that folder is loaded, you can see the files in that folder. We can start by looking at host.json. Host.json contains some information about application insights and logging. Local settings.json contains all the environment variables that you can pass to your function. So, for example, we pass an environment saying we want to use deployment runtime, development storage. And we have our C# source file. And you can see that the function is basically just a method. The function name is passed via an annotation here. So tracking input was the name we gave the function. The method is called run. It uses an HTTP trigger, which is also annotated here, which uses authorization level anonymous, accepts GET and POST requests. And what the basic initial setup of an Azure function with an HTTP trigger will do, it will try to read the name from the query, so from the URL. It will try to read a data point called name from the body of the request, and if a name is given, it will display a message with that name. And if no name isn't given, it will display usage message. So now we've created everything. Let's go back to the terminal and try out our function. So we're in the right directory, and what we can do now is just func start, and this will start the Azure function. Now you'll see that the first thing that happens is a build, and build doesn't take long, and then the function is started, and you get some information, and you can see that there is a function that was found, and you can see the functions inside that function host, and you can see there's the tracking input function accepting get and post requests at that URL. So let's copy that URL and go to the browser and call that URL in our browser. So copy that URL, go to the browser, and if we just call that URL without any additional parameters, what we expect is to get a usage message that tells us how to use the function, which is great because our function works apparently. Now let's add a name to the URL. Let's say name equals DPS 2021. And then we can see a message, a personalized message using that variable that we passed on the URL. So this is really great, and we've set everything up. So the next thing to do is to add some logic to that function. I've now added some logic that I would like to explain to you. So our function is still the tracking input function, but what has changed is that in our call we've added a so-called binding, output binding. So we've added a reference to a cloud blob container in a storage account called my storage account, and that container is the container that will contain the raw tracking data. So as you will already notice, this is not exactly what's in the architecture, but it will give you an idea of how difficult it is to implement all this. We've also removed the post from the allowed methods, so our function will only accept get messages, get calls. And the first thing we do is we get from the query, we get the session ID. Then we get the time when this function was called, and we add some error handling for the session ID. So if the session ID is not set, we'll just throw an error because this is something that cannot come from our application. Now in our blob container, we say, okay, the blob container is also contains the blob raw data, and if that doesn't exist, we'll create it, and inside it we'll create folders for year, month, and day. Next, we'll get all the parameters from the request into a dictionary, and we'll define the file name that contains the session ID so that we know that all calls that come from one session are within one file, which helps us analyze the traffic one user creates, as opposed to having all sessions in one file where we need to query all the files to find out which file contains data from one user. So this is something that we design, where we design the storage structure according to the needs of the analytics. Now, next we get the reference, an append blob reference for that file. So we get a blob that we can append to. If it doesn't exist, if this file doesn't exist, we create it, and otherwise we just append the data to that blob, and we give a success message. So let's start the function now, try it out. What I've had to do in addition to changing the code is I had to create a package reference, so add the storage package to my project, and I had to add the storage account connection string to my local settings. Now my function is running. Let's call it again. And again, I'll call it first. I'll call it without the name, just as it was, and I get an HTTP error of 500, which is what I expected, because if I don't pass a session ID, I expect there to be an error because I raised an exception, and I can see that exception in my log. So that worked as designed, even though it raised an error. Next thing that we'll do is we'll call the function and pass on a session ID. So let's go back and pass a session ID to our function. So add the session ID to the URL parameter. I've done that before, which is why it's already in my browser history, of course. And I call that, and I get the message appended to blob for session ID ABC123. So let's have a look at that file here. I can see the logs as well, that it all was successful. I can't see any further error messages. So let's now have a look at that blob file. So I go to my storage account and I navigate to containers and I open the raw data container. And in that raw data container, I should find a folder for the year, folder for the month, folder for the day, and then the tracking file, which was just created. So let's download that file, open the file and then download it, and then have a look at it. Open it up in Visual Studio Code. What happens if we open up that file, if we have a look at it in Visual Studio Code, is that we can see there's one message that contains the session ID, which is basically what we anticipated. However, now, of course, we don't only want to pass session IDs, we want to pass more information. So we want to pass information, for example, we want to pass information what pages were visited. So we can add a parameter called page and say what page was visited, product details page, and then I can add a parameter for the product ID and also pass that product ID. And if I call the function with that, and then go back to my storage account, I can see that my file, if I refresh here, I can see that my file has changed. So now the last modified time is later than the creation time, which is to be expected because I added to that file. Now I can download the file again and open it again in Visual Studio Code. If I look at the new file in Visual Studio Code, what I'll see in that file is a file with two entries. I'll see the old entry and I see the new entry appended to that. So that way I could design an API that gets data from the database and then logs the raw information via a storage queue, of course, but accessing a storage queue is basically the same amount of code as shown here. So we've chosen the shortcut to adhere to the time limitations of the session. However, the number of lines of code don't change significantly if we write to a storage queue and then you copy that code that we have here to the storage queue. So basically you've seen that this shortcut, that all of this stuff can be implemented in like 50 lines of code, which is rather neat and rather nice and small implementation for something that is rather complex, especially if you want to scale it according to the load you have on your application. So with that, we reach the end. Thank you very, very much for attending my session, for taking time out of your day to listen to what I have to tell you. And of course, a huge thanks to the DPS team, who are doing a really great job to create a really great conference here. And I hope you enjoy the rest of the conference and have a great day. Thanks for attending my session. Goodbye.